So, after the somewhat hard exam, let's start today's lecture with solving a much easier quiz. Right? The quiz was really easy. I hope everyone solved it correctly. Let's first figure out the direction of the induced current. Now, what was our rule? Well, it's not even a rule, it's called a law. What are we going to use to determine the direction of the current? Lenz's law, right? So that's now, first we have to figure out B of t, which is B0 e to minus 5t. Is this decreasing with time or increasing with time? Clearly, the magnitude of the magnetic field is decreasing with time. Good. Then the flux through the loop. How about that? It's also decreasing with time, right? The area of the loop stays constant. So the flux is decreasing with time. So what does Mr. Lenz tell us? He tells us that the loop is going to resist that change, which means B loop should be in the same direction as B, which means it's coming towards me. Okay. If B loop is coming towards me, then the current must be clockwise or counterclockwise? Counterclockwise. So I loop must be counterclockwise. Good. So we agree that this is what the current will look like. Now, how do I find? I found the direction, now I need the magnitude. I need to find out what exactly this current is. And what was, when we actually put some meat into this Lenz's law, make it quantitative, the EMF, the electromotive force created by flux was minus d phi dt. So what is the flux through the loop as a function of time? Okay, that's the definition, you're right, B dot dA inside the loop. In this case, magnetic field is constant. It's just going to be B times the area of the loop, which is pi r square times B0 e to minus 5t. So can you tell me what the electromotive force is in this case? It's going to be d by dt phi b of t. Pi r square and B0 are constants. I'll just take them outside the derivative. So it's going to be 5 pi r square B0 minus 5t. That's the electromotive force. How about the current? That's it, right? The loop current will be the electromotive force divided by the total resistance of the circuit, which is going to be apparently 5 pi r square B0 over r e to minus 5t. All right? How many of you reached this answer? Okay, maybe we should start studying now that we have seen that our second midterm grades are not so bright. Maybe, the remaining 3 weeks we can study more physics and get a much better grade in the finals. I think you guys are seriously disappointed in the second exam. That's the feeling I get. That's life. So You see, I'm lecturing, so I'm much more comfortable with your grades. I'm not the one getting the grades. So again, that's my attempt at humor, but today nothing is working. Now, I'll make sure I'll announce the grades after the lectures next time, okay? Let's solve one more example. And maybe talk a little bit more about forces and how induction actually creates this current. Now, I have sort of introduced this problem in the previous lecture, but let me do it again. So here we have two frictionless rails, okay, and a rod with negligible resistance. So I tie it to a resistance R. I'm also going to tell you what's the length of the rod between the rails. And I put the system into a constant magnetic field. And here's what I'll do. I'm going to make it move with velocity v as shown. Okay, so the rod is moving with velocity v as shown. I want to calculate two things. First, calculate the current in the circuit. Now, when I say this, when someone asks you to find the current, you must give the direction as well as the total amount of the current passing through. Okay? So I will not actually separately state that. And as the second thing, find the force that is needed to keep the rod going with velocity v. Again, I'm asking the force, which means you should also find the direction and the magnitude of the force. Okay? Now, first of all, why is there any current in the circuit? Let me redraw this maybe a little bit more quickly. What's happening when the rod is moving with velocity v? The area of the loop is changing with time. Okay, so if the area of the loop is changing, so area is changing, which means flux is changing. So if the flux is changing, there must be induced current in that loop. Let's first try to find out the direction. Now, external magnetic field is coming towards me, B. B, let's call this external, is coming towards us. Is phi of t, the flux through the loop, increasing or decreasing with time? It's increasing because the area is increasing. So what does Lenz's law tell us? It tells us that the current or the loop should resist this increase. So B loop must oppose B external. B loop must be into the page. To create a current into the page, my right hand tells me that I loop is clockwise. All right? Good. At least we've established that I loop is clockwise. Good. Now, let's calculate the amount of the current. Now, what is the flux at any time through this loop? Well, I know one side of my rectangular loop is L, but the other side is actually changing with time. Let me call this x of t. So the flux through this loop at any time would be L times x of t, where x is the position of my rod on the rails, times magnetic field, which is constant. Right? Now, what is the electromotive force created by this flux? It's minus d phi t dt. Now here I have L and B, which are constants, dxt dt. Okay. What is the derivative of position with respect to time? That's the first thing you learned in Physics 101. This is the velocity. So this is going to be bv times L, the electromotive force induced by this rod of length L moving it velocity v in a magnetic field B. Good. Now, how about this minus sign? Do I actually need it? It's just there to remind me of this Lenz's law. Okay? If I actually use my Lenz law, if I've already determined the direction of the current consistently, then what I'm going to need is just its magnitude divided by the resistance R. Yes? We could have, just without any problem, we would get a minus sign there, and its absolute value would be the same again. Here, there are two minus signs canceled each other, so I did not actually go over it again. Okay? Okay, so that's the thing. Once you determine the direction of the current, do not give a negative answer. That means actually the current is going the other way. Try to give always a positive answer. So if you actually, that's good, but it's probably not going to be graded. Okay, so what we want you to is to determine the direction of the positive current. That's, at the end of the day, that's what you should do. Okay? Good. Now, what does that give me? B times V times L over R. Cool. But here's the thing. Let me see. Here is my magnetic field, and here is my current, I. If I have a wire carrying current I under a magnetic field, there is a magnetic force acting on that wire. Right? Let's find the direction of the magnetic force. What's the direction of the magnetic force? F is I L cross B, where L is this vector. So L cross B. Which way does it go? L is down. I should orient my palm towards the second vector. L cross B is to the left. Okay. So the magnetic force acting on this rod will be to the left. So if I did not apply any force onto this rod, if I actually gave it an initial velocity v, what would happen? This force will slow it down, so my rod will slow down and stop. Okay. So to keep it going with velocity v, Newton's first law tells me that I should supply a force so that the net force on my rod is 0. So I must counteract this magnetic force by applying a force. I need to actually pull this guy, pull this rod with some force F. So let's show it. The external force, F external, must be to the right, and F external magnitude must be equal to F magnetic magnitude. So it's going to be I times L times B, and I have already found what I is, BV L over R times L times B. This is F external. So it's going to be B square L square V over R. Now, let's discuss what's happening in this circuit. Here's my circuit again. And I am pulling with this F external, which creates a current I, and here is a resistor here. If a current is running on the resistor, what does this cause? It causes, okay, maybe even red, this resistor will heat up, right? How much power will be dissipated on the resistor? The power on the resistor? I square times R. And I have found the value of I. It's BVL over R. So it's going to be B square V square L square over R square times R. B square V square L square over R. So this is the power on the resistor. That's how much I'm heating the air, if you want, with my resistor. But where is this power coming from? Where is the energy dissipated on the resistor coming from? Is it created by the magnetic field? But you remember, magnetic field itself never does work on charged particles. Its force is always perpendicular to the velocity, so it never actually does work. But here, I have F external acting on a system that's moving with velocity v. I'm actually applying a force. What's the power applied by whoever is pulling this resistor? It's going to be F dot V, right? So what's F? It's B square L square V over R times V, B square L square V square over R. Wow. So what does this device do? I am supplying mechanical work. And this device, the magnetic field actually, converts that mechanical work first into electrical energy, this current, and the resistor changes the electrical energy into heat. Okay, so magnetic field is a great way of converting electrical energy into mechanical energy, or just the opposite, mechanical energy into electrical energy. Okay, actually in the EE curriculum, I think there is a course called electromechanical energy conversion. Okay, that's a very fancy name saying for electric motors and generators. Okay, but actually this is called a linear, okay, this is a version of a linear generator, by the way. If you can pull something for a very long time, that's a way to generate electricity. Now there is a reverse object that's called electromechanical railgun. So, and this is a real object, okay, that may one day replace the chemical guns that are on ships. You know, on the ships, how do you actually fire a gun? On each payload, there is some, you know, explosive that explodes, that creates a lot of pressure, and it actually sends the bullet or whatever it is you're throwing, the warhead with high velocity. Now the electromagnetic railgun works on a much simpler principle. It says, hey, let me put this rod again, but this rod is going to be my warhead, or if you want, maybe it's going to propel the warhead or the bullet. Okay. Now, let's put this in a magnetic field, constant magnetic field. And here is the logic. If I run some current through this conducting rod, okay, and if I run it in the correct direction, and I think the correct direction here is going to be up, there will be a force F on my rail, on my rod, which is going to push my bullet. Okay, so the logic is that if I take a voltage source V here, and the switch, when I close the switch, a lot of current will run through the circuit, there will be a lot of force, and I'm going to accelerate my bullet and fire it. Okay? But let's say all circuits have some internal resistance. So let's say there is the internal resistance R of this circuit. Okay? What will be the maximum velocity achieved in this electromagnetic railgun? What is the maximum velocity in this railgun? I'm given V, R, and also magnetic field B, also quite possibly the length here. Now, when I first close the circuit, the rod is not moving, so there is no induced EMF. Okay, the presence of the magnetic field does not change anything. Instead, what we see is just there is a current on the rod, there is a force which is moving the rod. But after a while, the rod will be moving with velocity V, which means there will be an induced electromotive force. Right? So let's do that. Okay. if the rod is moving with velocity v, it acts like a battery, right? It acts like a source of EMF. And which way is that battery going to be? Well, you can actually think about Lenz's law without going to the details. Obviously, the loop is trying to resist the change of flux, which means increasing flux, it actually wants to decrease flux, it actually wants to decrease the current running in the loop. So what will happen? The battery will oppose, the virtual battery if you want, the induced EMF due to the rod will oppose the original battery that's driving the current. Okay. So what will be the electromotive force of this battery? It's going to be B times V times L. That's what we found. And here I have voltage source V. Maybe I'll try to capitalize it. If V is equal to B times V times L, no current flows in the circuit. If velocity is larger than that, what will happen? If velocity is larger than that, then the current will flow in the reverse direction, which means my rod will slow down. If velocity is less than that, there is still force pushing in the positive direction, so I will try to reach that critical terminal velocity in that system. Okay, so the maximal or the terminal velocity in the system will be V divided by B times L. Now, here's the thing. We did not actually put in the numbers, or we did not actually consider how this object is accelerated from rest. Right? If I have a very heavy bullet there, if I'm trying to, send a nuclear warhead using this device, which is presumably very heavy, okay, then I will need a very long rail gun. It has to be really long. But the nice thing is, if I have enough of rail, okay, I can actually excite my projectiles to very high velocities using this device. Okay, and you're really basically limited by how much power you can supply to the circuit. And also these railguns are extremely efficient. In a chemical reaction, only at most 20% of the energy that's going out in the explosion turns into the kinetic energy of the projectile. Here, if you have a circuit with very little resistance, then you can actually have most of the energy you're supplying to the circuit turning into the kinetic energy of your projectile. So what you can do is you can go to YouTube and search for railgun, and I'm pretty sure you'll be impressed by the videos you'll see there. And actually, I think last year someone tried to build one as Physics 102 project, but I don't know how that came up. Okay. Now, but here, so I've maybe picked the use of induction, which is the most terrible use of induction, right, to make a gun. Induction actually is extremely useful. It's used almost everywhere. Okay. When you're parking at Bilkent, I don't know if the student parking has the same thing, but every morning I need to show my ID to some device, right, to open the gate for the parking space. How does that work? Yes. Right.
I know a bit, but not all. But I think the magnetic field causes a reduction current, which gives the signal back to the.
More or less, yes, that's how it works. So the nice thing here is that there is no battery in my ID. Instead, what it has is, if we break this down, there are large current loops here. Okay. Maybe you have seen those loops if you actually buy some theft-protected object from Real, or maybe inside the books, you can see all these loops. Okay. So how does that work? When I show my ID to the reader, card reader, there is a fluctuating, there is an oscillating magnetic field there. This oscillating magnetic field actually creates a current here, which powers the very simple electronic circuit here, which gives back a signal. Okay, it tells. The only thing that electronic circuit does is that it gives back a number. It says this ID belongs to 6262, like my number, Bilkent number. And then whatever else the device, the parking device says, okay, 6262 has access to this parking lot, so let me open the gate. So this is one use. Another use is, it's becoming even more current now. Most new cellular phones have wireless charging. So there is a base, you put your wireless phone on that, your phone on that, and it starts charging. And how does that work? Again, induction. Okay, for those phones there is a big loop here again, which picks up this oscillating magnetic field and charges the battery. There is another very simple use. We've been talking about ancient cities, Manisa, Magnesia. There are a lot of ruins in Turkey. So one of the most popular pastimes of a Turkish villager is to hunt for treasures, right? What do? They buy a metal detector. Okay. How does that work? How does a metal detector work? And it doesn't have to be buried treasure. How do you find if there is a metal here and there is this device, a metal detector? Again, a military use is to detect mines. Okay. So this metal detector does actually something very simple. It creates an oscillating magnetic field. That's it, more or less. Okay. Now, if you have a metal, not just a let me try to draw something easier. Let's say that I have a piece of metal and it actually sees some magnetic field which is non-uniform and which is changing in time. Now, a metal is conducting at each point. So you can actually start running currents on any point of the metal. So when you actually expose a metal to a changing magnetic field, small loops will form. Okay, there will be loops of current forming inside your metal. These are good if you want to detect a metal. These are called eddy currents, by the way. They will create a back action. They will create a back magnetic field, which your detector will pick up, and the detector will start beeping, saying, "I'm getting some eddy current signal." That shows metal. Pretty much whenever you go to any secure place, including this building, right? There is a metal detector which is not working somehow at the entrance. What does that do? It basically sends or makes you pass through an oscillating magnetic field. If you actually have a loop that's resonant with that frequency, or if you have a big chunk of metal on you, that's going to give back a signal. Same thing applies to mine detection. Unfortunately, I learned some years ago that people have, even in the 1980s, 1990s, figured out that if you make a mine out of metals, it's easy to detect. So most landmines today are made up of plastics. Terrible use of technology, but that's it. Another use of eddy currents is, or maybe a bad thing about them is, if you run currents in a metal, what do? They heat up, right? Now, that may actually be a big problem. If you have an oscillating magnetic field somewhere, it may cause a lot of heat to be generated at certain points. Okay. So, for example, these magnetic resonance devices, MRs, okay, it's a great medical use of the technology. They have oscillating magnetic fields, and by some miscalculation or by some chance, if someone leaves a metal near it, even if it's secured so that the forces are not important, there will be so much current on it, it can actually melt. There is something called an induction furnace. You can put a piece of metal in a very big and oscillating magnetic field that's going to melt the metal. Okay. I cannot really, I mean, induction is a part of our daily life. It's being used everywhere. When I talk about AC currents, I'll talk about how they are generated a little bit more. I'll also talk about how they are transformed from one voltage to the other. So transformers also work on this principle of induction. But let's wait for one more week to talk about that. Okay. That's it for this lecture. We'll continue in 10 minutes.